All right, so 16 is what we're going with. World record 100-meter race, Maggie Judy, at 9 seconds. So what is that? What do they have to therefore share in common? No, different velocities, but same average velocity. Same average velocity. Assuming they're both starting at the same point, ending at the same point, starting at the same time, ending at the same time, right? So their average velocities are the same, but that doesn't mean their instantaneous velocities or their accelerations are the same. Given that they're accelerating uniformly, we can use our relationships that have to do with uniform acceleration, the ones on our equation sheet. Maybe we should bring that up to make sure that we have it. Right? Just get used to referencing that. Let's see. All my stuff. So we can use our 3 up here that are our constant acceleration equations. Keep in mind, those only work if the acceleration is constant, right? Non-time dependent, non-velocity dependent. So we can use those relationships that we're maybe a little more familiar with. And so let's look at what was the acceleration of each sprinter. Okay. So attain maximum speed, which they maintain for the rest of the race. So I'm getting in my mind that if I drew the race, here it is, that's 100 meters, that's 0 meters, right? Maggie, we'll make Maggie red. She's going to run for a certain amount of time, and at some point here, this is where her V is a max. And then she maintains, so acceleration here, acceleration equals 0 here, right? And there's some point in here, which is actually 9 seconds before the end of the race, that she hits her maximum velocity, right? And then she maintains that for the rest of the race. And same thing with Judy, but she did it at 2.7 seconds and hit the maximum speed. So let's look at what's going on here. So for the first, so I'm going to look at Maggie here real quick. For 0 times greater than 0, but less than or equal to 2 seconds, we have one equation, Maggie's velocity, where she's accelerating, and then from greater than 2 seconds to less than or equal to 9 seconds is when the acceleration for her is 0. So we have to look at them piecewise, right? To get where they are and everything else about them. We know that, well, okay. So you can do a couple relationships here. For the first, let's call this section 1 and we'll call that section 2. For section 1, we can use our definition of velocity. We can use the fact that V final V initial plus AT. Remember, that's just a rearrangement of our definition. Actually, let me go back, sorry. We'll go right for it. Acceleration is change in velocity over change in time. And so we can say that V final equals V initial plus A delta T for that first 2 seconds. And so we can get an expression that says her velocity at 2 seconds, this is 0, equals her acceleration times 2 seconds, or 2A in seconds. I know, why am I doing that right away? I'll show you. Because I want to be able to describe her displacement in the parts. So her displacement total, displacement of A, is going to, like both, equal 100 meters. But it's going to be made up of displacement after 2 seconds plus the displacement from 2 to 9 seconds. And that will equal 100 meters. Her displacement for the first 2 seconds is going to be controlled by the fact that she is accelerating during that, and her displacement for the next is going to be controlled by the fact that she's not accelerating for that. All right? And you'll see how this works out. So for here, I'm going to use, we do have that equation. I'm going to use our second equation here, x equals x naught plus v initial vx naught t plus 1/2 ax t squared from previous years, right? So in here, I'm going to put there we go, look at that, we can see both at once. In here, for the 2 seconds, her initial position is 0, right? Actually, I don't need to worry about the initial positions because these are actually distances, not displacement. Her initial velocity for the 0 to 2 seconds part is 0, right? So that takes out that whole term. The second part is 1/2 whatever her acceleration is, and then 2 squared plus, now how far she moves in the second part will be the x again, x naught we don't have to worry about because we're adding the distances. Her v initial, which we'll call v2, times t, which is 7, plus her acceleration, which there isn't any, right? No acceleration, so equals 100 meters. Well, now we can, in here, we can substitute our 2a. So we're going to have 1/2 a times 4 plus 2a times 7 equals 100 meters. And that'll give us 2a, 16a equals 100 meters. So her acceleration is 100 over 16. That should be in meters per second squared. And whatever that comes out to. Is that the first thing they ask us? Let's see if we got it right before we go on. You want a shortcut in I'm being lazy. It will do simple math for you. Come on, be right on this afternoon. Yay! So, right back here. So that was Maggie. Now let's do Judy. Do you want a second to try Judy, or do you want me just to go through how to do Judy? You want a second to try Judy? Okay. I'm gonna pause. All right. So Judy, you set up Virtually the same way. Difference is the 2.7 for the acceleration versus the 9. Then you once you figure out the A, let's see, I'm going to do this on the calculator rather than my head. I'm going to have 100 divided by parentheses 0.5 times 2.7 squared plus 2.7 times 6.3 close parentheses, enter, and I get 4.8414275, which of course I'd report as like 4.84 meters per second squared. Should be that's 100 over 16. So I know what have the value in the back of my head. 6.25. So this is 6.25 meters per second squared. How did Judy come out? Good. You got it? Good. Okay. The more you can lay out your work nice and sequentially, the easier you'll find it going.
I just like got confused because I was using the other equation, but I got constant.
Then for B here, it's a substitute back into your beginning condition. Like for Maggie, it's going to be this V2. Substitute in now the 6.25 for A and the 2 seconds. So like Maggie's for mine is going to be 13 and a half. And then the same thing for Judy. So for Maggie, I'm going to substitute back in. V2 is her max. This was 6.25 meters per second. And multiply that by meters per second squared, excuse me. Multiply that by 2 seconds. And that's why I get V2 as 12.5, excuse me, not 13. 12.5 meters per second. That's for Maggie for me. Then I go down here and I'm going to do the same thing here for Judy. Substitute in my 4.841 meters per second squared at 2.7 seconds. And for Judy, she comes out and I run these calculators times 2.7. She comes out to 13.07 meters per second. And good on that. Who needs more on this problem? But I'm sensing some people are good now on it. Still need more?
I can probably figure it out.
Yeah, the next thing is just setting which sprinter was ahead at the 6 second mark. You go back to this equation here, the D plus D, and that's an unknown now, but you have your 2 and your 4 seconds, and you know more information now. So you figure out where each of them was at 6 seconds. All right? And since they finished at the same time, I'm going to guess it was Judy, because she has a slower maximum. So if she wasn't ahead, if Maggie wasn't ahead, if Judy wasn't catching up the whole time, they wouldn't have ended together. So I'm guessing Maggie. For which?
To find out
go back to here, and rather than the 100, you have an unknown now. But now you know A and you know B. And this 7 like turns to a 4. And it turns to a 3.3 in the other one. My guess, it should have been Maggie that's ahead as long as Judy's. Let me try that on mine. But I bet. Because you're figuring it out at 6 seconds. So I have 2 seconds. Then, yeah. All right. So number 12 here. Automotive engineers prefer a time change acceleration as the jerk. Suppose an object moves in one dimension such that jerk J is constant. So that means the rate that the acceleration is changing is constant. Determine the expressions used for acceleration, velocity, and position, given that the initial acceleration, speed, and position are respectively, and appropriate in your equations. Okay. So, everyone remember our symbol for jerk? N, right. So, we would put N to the T is a constant C. And then if we take the integral of that is how we get to the acceleration. So the integral of N with respect to T is A with respect to T, which comes down to C T plus a constant, and that constant is A naught, or A, what do they want, initial? Hard for me to read that. Let me see, hold on. Yeah, looks like initial. So that's plus A initial. I'm kind of taking the real shortcut integration here. All right. And then if I integrate A with respect to time, means I integrate C T plus the integral of A initial. I get V with respect to time, and I get C over 2 T squared plus A initial T plus a constant, which is going to be my V initial. The constant always comes out to whatever the initial condition was at time 0. So I'm kind of skipping putting the constant. It is the initial condition. And then once we get the idea here, then we'll make it all pretty to put into the computer. All right. If I integrate V with respect to T, I integrate these again, integrate them separately. I get position, which we're saying is X. This goes up to T cubed, which means I need to add a 3 down the bottom, which makes the bottom 6. And this stays at a constant C. Plus, I get A initial over 2 T squared plus V initial T plus D X initial, sorry. And if you didn't have that jerk in there, oh, that looks like 1/2 AT squared plus V initial T plus X initial. And for constant acceleration, that is it. But then when you have a jerk in there, you add in that extra term because you have the changing acceleration. So now all we have to do is make that pretty to put in. So integral of jerk is acceleration, integral of acceleration is velocity, integral of velocity is position. Each time taking into account how the t is what you're integrating with respect to, and bringing in those constants of their initial conditions. All right? Yeah, Ed. Well, now we got to make it pretty to put in. Okay, let's make it pretty. All right, so all of our C's should have been J's, and then they want us to show that A squared is A. And oh, that's kind of fun to do all that squared out. Do you want me to do that second part? I think you guys can probably do it as algebra. B. Or do you want me to tackle 9 or 11? What time we have left? Back to Mike? Yeah. No, I'm not going to collect it. Yeah. So this would be a really good idea to do because you really want to do well. No, but it's a type of thing that they would definitely ask on the AP to do. So that's where it would be a good idea to do it. I don't know if it'll be other than that. I'm going to change all my C's to J's since I have a moment. It'll just make me happy. Oh. Yeah, is that nerve-wracking?
Oh my god, huge work.
Alrighty, let's do number 9. Student set keys vertically to her sorority sister, who is in a window 30.7 inch while the caught 1.2 by her just to her hand. Was the initial velocity keys thrown. Of course, we're in free fall here, which gives us a constant acceleration, right? So we got the ground here, got the building, got the hand, we got the sorority sister. Accelerating down the whole time at G. So, let's see. Okay, which direction do you guys want to call positive? Up. Okay. Where do you want to call 0? Ground, 0 meters. Okay. All right, you got it. So, I'm going to use. I want to know the initial velocity. I'm going to use that x equals x naught plus vx naught t plus 1/2 at squared ax. There, of course, it's this. And I know that they end up at 3.7 meters. That is 0, because they start at 0. I don't know vx naught. I know my t, 1.40 seconds. Plus 1/2. I know my acceleration, negative 9.80 meters per second squared. And I know my t, 1.40 seconds squared. And I get a vx naught. Or vy naught, if you want to call it that. Why not? Yeah, why not? And then what was the velocity key just before they were caught? With that, I'm going to switch to my Vx equals Vx naught plus AXT. And I'm looking for Vx. I have Vx naught from earlier plus my negative 9.80 meters per second squared. And then my t is 1.40 seconds. Well, it's easy once you see it, but